The sport of high jumping had its most significant development at the 1968 Olympic Games in Mexico City, after an American athlete, Dick Fosbury, revolutionized his track and field event with a new technique which became known as the Fosbury flop. His innovative style captivated the crowd. Instead of leaping facing the bar and swinging first one leg and then the other over the bar, with a technique known as straddle, he turned just as he leapt, flinging his body backward over the bar with his back arched, following with his legs and landing on his shoulders. Such approach was considered dubious at the time. However, biomechanical analysis provided that this new technique was better and more proficient. The approach included an arc for the first time, which led to a faster and more successful clearance of the bar. Experts agree that the most important segment of the high jump is the approach. This film relates to its design and its analysis. A research done in 1994 provides data that can help us to improve the design of the approach. A special video analysis technique was used to measure the footprint locations of the top 8 men and 7 women in the high jump finals of the 1991 World Championships. The last successful jump was analyzed for each athlete, as well as the final speed of the approach and the final direction of motion of the center of gravity at the end of the approach. The path of the footprint in a high jump approach can be idealized as a straight line perpendicular to the bar, followed by a circular arc which ends at the takeoff. Such a path is defined by the position of the takeoff foot, its x and y axis, the angle between the bar and the final direction of the jumper's approach, and the radius of the curve. As you can see, in the transition to the curve, the athlete's body tilts toward the left. The tilt is maintained during the curve, and the athlete follows a path that is somewhat closer to the center of the curve than the footprints. At the end of the curve, the parts of the athlete and of the footprints converge, and this puts him more or less directly above the left foot by the end of the takeoff. A consequence of the convergence of the two curves is that the final angle of the athlete's path is always larger than the corresponding angle of the footprint's path. This film will refer to athletes who take off from the left foot. To make this film applicable to athletes who take off from the right foot, the words right and left should be interchanged. There are many ways to fit a circle to the footprints of a high jump curve. This film shows the use of the circle that passed through the takeoff footprint and made the best possible fit with the second, third and fourth footprints before the takeoff. Notice that the next to last footprint was ignored. The reason for this was that many jumpers seemed to plant the right foot in the next to last support outside the general curve, and therefore the inclusion of this footprint would have a misleading effect on the shape of the fitted curve. You can now see the footprints of the 8 athletes analyzed at the 1991 World Championships and the circular arc that was fitted to the curve of each approach. The drawings show that all the jumpers in the sample followed very closely the modeled circular path in the last steps of the approach, although, as expected, in several jumps the next to last footprint was clearly outside the general curve. Some jumpers, like Austin, followed very closely not only the curved section, but also the straight section of the path modeled by the computer. Other jumpers, like Drake, started the straight section of the approach somewhat farther outward than predicted by the computer model and later converged into the final circular path. Jumpers like Dalton Grant and Troy Camp make a sudden change in the direction of running at the start of the curve before settling into the final curvature of the approach. Drawing and designing the approach is not allowed in competitions. Nevertheless, athletes and coaches always strive for its perfection. As you can see, the following data are shown: the radius, r, the final angle of the jumper's approach, f, final speed of the approach, v, and the final direction of motion of the center of gravity, p. Patrick Sjoberg's values show the biggest radius and therefore the widest approach. However, Hollis Conway's values show the smallest final angle of the jumper's approach, therefore the smallest radius. On the other hand, Sotomayor's values show the highest final speed of the approach. These approaches show the wide range of values for the radius of the curve, the width of the approach, and the final angle of the jumper's approach. What does this mean? Coaches and athletes often test different approaches in order to find the best position for the takeoff. There are three main methods for modifying an approach. 1. Setting an athlete into the same final angle of approach by changing the width of the approach and the radius of the curve. This method is applied when the length of the approach, thus the speed, is changed. For example, for a 7-meter radius, a 4-step approach is suitable. For a 9-meter radius, a 6-step approach is suitable, whereas for a 12-meter radius, a 10-step approach is suitable. 2. While maintaining a constant width of the approach, change the final angle of jumper's approach by changing the value of the radius of the curve. Thus a jumper manages to find his ideal final angle of approach. 3. While maintaining a constant value of the radius of the curve, change the final angle of jumper's approach by changing the width of approach. What is the exact purpose of the circular arc? In the transition from the straight section to the curve, a force that tends to pull the body away from the circular arc affects the jumper immediately. This force is called the centrifugal force. A jumper then leans towards the center of a fictional circle, thus boosting the centripetal force. Centripetal force tends to make the body move towards the center of a fictional circle. However, an even balance of these forces puts the jumper in the optimal position for the circular run. Everything has to be optimal at the takeoff. The lean, the centrifugal and centripetal forces, the speed and the final angle of jumper's approach. At the takeoff, the centripetal force weakens and the centrifugal force increases to its maximum. As a result, the jumper moves away from the path he was following. With an appropriate takeoff and with a vertical lean, a jumper backed by the centrifugal force will overcome both the height and necessary depth of the leap. The proportion between the square of the running speed and the radius of the curve used by an athlete determines how much the athlete will lean. This can be expressed by the formula Q equals V squared over R. The larger the value of Q, the greater the lean. This means that an increase in V while keeping the radius constant will increase Q and the athlete will lean more. An increase in R while keeping the running speed constant will decrease Q and the athlete will lean less. Why is this important to take into consideration? After a jumper leans in the curve, his foot gets in an unnatural position. His feet and ankles are under tremendous pressure during this part of the approach, and he experiences foot torsion. So, considering an increasing amount of compensatory lean and final approach speed, a slip of the foot is likely to occur. However, the final approach speed will not be reduced since it's the most significant part of the approach. Therefore, the radius of the curve and the width of approach will be increased. As a result, the compensatory lean and the pressure on the jumper's foot will be reduced. How to calculate the appropriate circular arc for a specific jumper? The following instruments are necessary: a ruler, a compass, a protractor, a pen, and an A4 sheet of squared paper. 1. Draw a high jump landing area. The ratio is 1 to 100. 2. Mark a specific takeoff point. 3. Draw a specific width of approach of a jumper, the x-axis. 4. Draw a specific length of approach of a jumper, the y-axis. 5. Write down the distance from the first bar stand to the start point of the approach. 6. Using a protractor, calculate a specific final angle of jumper's approach. 7. Draw a tangent at the final angle of jumper's approach. 8. Put the sharp point of the compass on the tangent and draw a circle starting from the takeoff point. If the circular arc and the y-axis do not join, move the compass until the joining point is found. Nine. Carefully measure the value of the open compass. This value is the radius of the curve. 10. Put the sharp point of the compass on the takeoff point and draw a line on the tangent. The point where the two lines intersect is the center of a fictional circle. 11. Using a ruler, draw a line between the center of the circular arc perpendicular to the y-axis. The joining point is called the start of the curve. 12. Calculate the length between the start of the curve and the x-axis. Finally, all data from above should be multiplied by 100 and written down in a notebook. In the actual high jump run-up area, the calculation and measuring process should look like this. First, a jumper determines his takeoff point and marks it. Then he measures the width of the approach, starting from the first bar stand. Some jumpers prefer to do the measurement with their own feet, others use a measuring tape which is more accurate. The next step is to measure the length of the approach. At this point, certain problems may occur, since it's extremely difficult to set the length of the approach perpendicular at the right angle to the x-axis. Therefore, a second measuring tape is attached to the stand and stretched towards the specific value of the first measuring tape. The point where the values of the two tapes intersect is called the start point of the approach. While the tape is still on the ground, a specific value of the start of the curve is determined. Then, the tape is attached to the start of the curve and stretched until it reaches the value of the radius of the circle. Using a piece of chalk, the jumper then draws an actual circular arc. After that, the tape is attached to the takeoff point and stretched until it reaches the specific value of the radius of the circle. Again, the jumper draws an actual circular arc. The point where the two arcs intersect is called the center of the radius of the circle. Finally, the tape is attached to the center of the radius of the circle and the jumper is able to draw the actual curve from the start of the curve to the actual takeoff point. The complete approach is now designed and the training can start. Considering the fact that the approach is the most important part of the high jump, the aim of this film is to help athletes as well as coaches in designing an ideal specific approach which should enable them to achieve the maximum. The future lies in the young. Therefore, it is crucial to train properly from the very beginning. A precise training ensures excellent results and success as well. There should be no room for errors.